And so we can see we have three groups here. Their means are summarized in this row and their standard deviations in this row. And these all look somewhat familiar because we had computed them last time or the time before. And we're assuming with this data, as we did in the one-way ANOVA computation, that it's between subjects. So group 1 has 5 subjects, group 2 another 5, and group 3 a third group of 5 for 15 subjects contributing 1 observation each. So some highlights from last time. We found that we had an F value for this data of 2 and 12 degrees of freedom of 4.54. And we also had, as part of that computation, the sum of squares group. And I'm going to refer to sum of squares group a bit later, so it won't hurt to write it down now. And that happened to be 72.4. So this was the amount of variance that was attributed to the fact that we had a manipulation of these three groups. And then finally, we also had the MS error, mean squared error, from our ANOVA computation that made the denominator of the F-test. And that is equal to 7.967. All right, so this time then, what we're going to do is we're going to compute two linear contrasts. The first one is going to compare groups 1 and 2 together as a chunk with group 3. So what we'll be asking with that contrast is if on average the means of group 1 and 2 are significantly different than the mean of group 3. And then we're also going to compute a second linear contrast that just compares group 1 with group 3. So with that linear contrast, we'll be asking the question of whether this 1.8 is significantly different from this 7. So the first thing that we're going to do is we're going to write down what the formula is for a linear contrast. And actually a linear contrast, the way that we do it in class is we do an F-test, similar to the way a one-way ANOVA is an F-test. So the F associated with the linear contrast is the mean squared of the contrast, or the between group variation, over the mean squared error. And because we already computed the mean squared error for the one-way ANOVA last time, we have it in our arsenal. So we won't need to compute that again. But it is the same mean squared error that you would use in any of these linear contrast F-tests. So in order to make a mean squared contrast, you need the sum of squares associated with it, and you need the degrees of freedom. So we'll start with writing the sum of squares contrast, which actually looks a little funny. So it's little n times capital L squared, only the L is squared, divided by the sum of these funny looking AJs, and these individuals are squared before adding them. So it might help to go over what these are. This is just the number per group. This L is actually, it's L for linear combination, which is a fancy way of saying that it's a combination of the means, so 1.8, 3.2, and 7, and their weights. And we'll discuss weights in a moment. As a matter of fact, right now, these here, before you square them, are our weights. So in the formula, it's the weight squared. All right, so let's start with contrast number 1, which is the question of whether group 1 and group 2 on average differ from group 3. First thing we're going to do is we're going to form our big L, our combination of the means and the weights. And the way that we have to choose the weights is so that it's understood that group 1 and group 2 will be completely oppositely balanced with group 3, because group 1 and group 2 are together in this chunk versus this other chunk consisting only of group 3. We want to kind of compare those against each other. So the way that L looks before you put any numbers in is your first weight times your first mean plus your second weight times your second mean plus your third weight times your third mean. And so in order to compare group 1 and group 2 against group 3, one selection of weights would be to make A1 1 and to make A2 also 1, but then to make A3 not -1 but -2. That way there's -2 units of weight assigned to this chunk and then +2 units of weight together for this chunk. And so this is the type of L that we need to create. Phew, almost made a horrible mistake, but we caught it. So now we have that our L for the first linear contrast is -9. So we're going to be able to sub that into the numerator for the SS contrast formula. But we also need N. We know that N, being the number of observations per group, is 5, as it has been in our previous computations. And we also need the sum of the squares of the weights. So if you can recall, we had 3 weights, 1, 1, and -2. And they were A1, A2, and A3. So to create this denominator for SS contrasts, we will just sub in our weights and square them, and then sum them. And I remember this is a -2. And so when we compute what that is, we get 6. So now we're ready to compute SS contrast. So N is 5, L is -9, which gets squared. So if your L is negative versus positive, it won't make a difference in SS contrast, which is good because maybe there was a different way in which to choose these weights and it resulted in somehow a positive number. I'm not sure when that's possible, but it's good to know that it doesn't matter if there's a negative sign there in the end. It means you're doing it okay, probably. And then we divide by 6, the sum of the squares of the weights. And then we get, let's see, 405 on the numerator divided by 6, so 67.5. We can understand as contrast this number as being kind of a subset of the variance explained by the fact that we have 3 groups, by the between group variance. And to help illustrate that, if you take a look at SS group, it's 72.4, and SS contrast for this contrast is 67.5. So it's a kind of a great proportion of that variance can be explained by saying that group 1 and group 2 are different from group 3. But in fact, we should probably calculate the F first instead of just assuming that 67.5 being pretty big is going to give us a significant F. Let's actually do that. Our first thing is we are going to compute mean squared contrast. So mean squared is SS contrast divided by degrees of freedom contrast. However, think back to how we put one chunk opposite another one, and how when we do these linear contrasts by hand, that's exactly what we're doing. We're taking 2 different chunks, and some of the weights are negative and some of the weights are positive, but in the end, you're taking a chunk from these groups and comparing it to one other chunk. And because of that, the degrees of freedom are always going to be the number of chunks minus 1. And the number of chunks that you have is always 2. So the degrees of freedom is always going to be 1 for the contrast. So an mean squared contrast actually equals the sum of squares contrast. It equals 67.5 over 1. Okay. So far, so good. Finally, we compute our F statistic. F is equal to the mean squared contrast divided by the degrees of freedom contrast, which, oh, just kidding. It's not divided by degrees of freedom contrast. F is always mean squared of an effect divided by the mean squared of error. So I kind of slipped there. Hopefully that woke you up a little bit. Or maybe you caught it and you were like, no. So yeah, so F is always mean squared of an effect divided by mean squared of an error. So if I were to put a degrees of freedom down there, I would have made an error. So that is equal to 67.5 divided by a mean squared error, which has been conveniently hiding out over here, 7.967 from the ANOVA. And here, that gives us to 3 decimal places 8.472. So that is the F value. Usually we report them rounded to 2 decimal places, so 8.47, associated with group 1 and group 2 being compared to group 3. It's a pretty high F. I'd be willing to bet that that is significant. So now we've got a bit of a handle on things, or at least you don't, but you have a better idea of what you're not getting than you did before you watched with me. So now we're contrast 2, we're gonna compare group 1 and group 3, but we're not gonna consider group 2 in that comparison. Almost kind of like we're doing a t-test. Pretty similar to doing a t-test. The math looks a little different, that's all. So the first thing we're going to do is we're going to have to create our combination of means and weights. The means are going to be the same, but the weights are going to be different this time. So I'm going to call them little b's instead of the a's that I was using before, just to avoid any confusion when we have to discuss them together. So for this one, take a pause. Think about what you would want the weights to be if we were going to pit group 1 in a battle royale against group 3, and group 2 would not be in said battle royale. And I went with 1 times mean 1 plus 0 times mean 2 plus a negative 1 times mean 3. There's a little typo here that I found too, that this subscript was meant to be for mean 3. I think you guys knew what I meant, but we caught it. Yes. Okay, so then we just do the computation. All right, we've established that for our second contrast, comparing group 1 and group 3. L is negative 5.2, N is still 5, and the sum of our weights is equal to 2 this time. So we'll just sub that into the SS contrast formula, see what we get. So our SS contrast then is 67.6. And finally, our job is to find the F ratio. We can do that right away because the degrees of freedom contrast being 1 means that SS contrast as a number is equal to MS contrast. This time our F ratio was 8.485, which again seems quite a significant F to me, though I'd have to check with the table first. And so it seems that group 1 and group 3 are significantly different from each other. Again, getting some deja vu from t-test time. So this F is very, very similar to the F that we got before. The F that we got before was 8.472, so there's hardly a difference, and that's of course due to the fact that these contrasts both summed up to quite a large amount. So here's the idea. We computed two contrasts. One of those contrasts compared group 1 and group 2 together to group 3. And the sum of the squares associated with that kind of variance was 67.5. And then we compared group 1 and group 3 in a second contrast, and the sums of squares associated with that variance, the comparison between group 1 and group 3, was equal to 67.6. So, first thing, I have a question for you. My question is whether the contrast 1 and contrast 2 that we built are orthogonal to each other. The answer to that can be determined using a test, using the weights of contrast 1 and contrast 2 together to see if they are orthogonal. And they would be only if A1 times B1 plus A2 times B2 plus A3 times B3 was equal to 0. This is different from just the sums of the individual weights for a contrast being 0. That definitely does have to happen. A1, A2, and A3 summed together must equal 0, as does B1, B2, and B3 summed together. However, this is different. This is a test to determine if the two contrasts are orthogonal. So let's test. So we have our answer then. No, contrast 1 and contrast 2 are not orthogonal, using the tests that we have available to determine whether contrast 1 and contrast 2 are orthogonal, more in a mathematical sense. Conceptually, again, that means that they are in no way related. But why is that a problem? So here's the meaning of what we're doing here. We are always looking at chunks when we do linear contrasts. For example, we chunked up our means into group 1 and group 2, and then another chunk for group 3. So there were two chunks here. There always are. Now, if you think about it in terms of chunks, the largest chunk that we have, the most complete one available to us, is actually the chunk that's formed by all the groups. So while that would be kind of a useless chunk to use in a linear contrast computation, not sure how that would work, it illuminates for us that the largest chunk then is represented by sum of squares group, which was found again in our ANOVA that we did in the last video. The 72.4 is the biggest amount of variance that can possibly be attributed to the groups because it is SS group. It's maximal by definition. So if we end up having a contrast 1, which say happens to equal 67.5 for its sums of squares, that is, and if we have contrast 2's sums of squares as 67.6, which is kind of eerily close, then when you add those two up together, right, you don't get something less than or equal to 72.4. In fact, the sum of these two numbers is 135.1. So that's a bit of an inflation of the numerator of any kind of f-tested. So these contrast 1 and contrast 2 do not work well together because they do something called oversampling the data or kind of inflating how much SS group really is. So to summarize, we were talking about as well as finishing with how we can avoid oversampling when we are determining the linear contrast we'd like to compute on our data, is that when you start out with your first pair of chunks, say group 1, group 2 versus group 3, then in the next contrast after that, you may only split up at one chunk on one side. So you can either split this chunk up or this chunk up. You have to kind of follow one path, so to say. However, when we try to do a schematic of what we did today, we've split up into two chunks, group 1 and group 2, and then versus group 3. And then instead of just focusing on splitting up one of those chunks some more, we've taken again from both of those chunks to create new chunks. This is group 1 versus group 3. And so we now have a way that we can avoid oversampling, and that is to follow a single path down a contrast tree. And my final remark to you, besides well done for hanging in there and working through the contrasts in a hand calculation with me, is that there's a maximum number of contrasts that you can do this way. Here now we ran out of contrasts to do. And in fact, if you have 3 groups and 3 means total, then the number of contrasts you can do is 2. If instead we had 4 groups and 4 means, then the maximum number of contrasts we'd be able to do before running out in the tree would be 3. And so, as you may recall from class, there is a general rule to that.